This is video 3.4.C, the third video in the series about intermolecular forces. And this video should be short because it's only about dipole moments. So it should only be a moment long. No, not really. It's going to be, but it should be short. Because by the end of this, you're only going to have to do a couple of things. You should be able to define what a dipole moment is, and then you should also be able to identify where a dipole moment would be for any sort of polar molecule. So, in terms of definitions, I wrote that definition down up top there, and you should be able to look it up. But the idea is a polar molecule should have a measurable quantity that tells you that it is polar. Bond polarity, you just have to look at the electronegativity differences. That difference, that's a measurable value, that tells you if a bond is polar. A dipole moment is the same sort of thing, except it's the measurable quantity for a molecule's polarity. Now, the fortunate thing is that we're never going to have to be able to measure it or put it in our dipole moment machine and measure anything in this class. All we need to do is be able to indicate where the dipole moment is on polar molecules. So we have water here, and water is a polar molecule. Water has a partial negative charge on this side and a partial positive charge on this side. We have O and H. Oxygen is more electronegative than water. And so if we draw the kind of split this in half, you'll see that there's a polar molecule here. There's a pole up here, the negative pole, and the positive pole down here. And how we indicate the dipole moment is with an arrow that could be moved in any direction. It kind of looks like this. So this arrow, it's an arrow here. Then it's got a little hash mark down here because that's the positive side. This is actually showing the direction of electron movement in the molecule. But for our purposes, let's just keep it as an arrow with a little plus sign at the bottom. So for water, for the water molecule, oh, look. For the water molecule, the arrow will be pointing straight up here. And that's a positive charge down here. Now I took ammonia, and now I have the three-dimensional ammonia molecule. Maybe this will help us see what it looks like in 3 dimensions. So this is N, H, H. The electrons are up here. Now, there is an electronegativity difference between nitrogen and hydrogen again. So that electronegativity difference means the molecule is polar, coupled with the fact that it is an asymmetric molecule. So where is the dipole moment? Well, in this molecule, when we take a look, we see the hydrogen's kind of at the bottom. So the dipole moment goes up and through there with the positive, that positive thing at the bottom of the molecule. So now let's try it yourself. Pause the video and see if you can figure out where the dipole moment is for each of these molecules. You may have to draw it on a separate sheet of paper. Okay, assuming that you pause the video, here's what we're going to do. We're going to draw the dipole moment. Now, oxygen, more electronegative than sulfur. That's what these values are here. Okay, and so we're going to draw the dipole moment with the positive arrow being on the sulfur, or closer to the sulfur side, because this is the partially positive and these atoms are partially negative. So now we have bromine pentafluoride. This one's a little bit more interesting. So here, what we're going to do is we're going to draw the arrow going right up through this with a positive side down here closer to bromine. Now, I am going to take and I'm going to move some of this stuff out of the way because I want to show you this in 3 dimensions. Okay, so what I'm going to do is I'm going to pull down this guy. This is a square pyramid. This is exactly what bromine pentafluoride looks like. Each one of these points is a fluorine, and then there's one up here. And the bromine is on the bottom here. Now there's a couple of electrons down here, so that's what makes it asymmetric and polar. But what we see is that these fluorines kind of cancel each other out. This one is kind of canceled out by this one, and this one's canceled out by this one because of symmetry. And so we really only have a dipole moment that goes right up through the pointy part of the pyramid, with the positive side being the bromine, because bromine is less electronegative than fluorine. So that's your little tutorial on drawing dipole moments.